For Module 2, Lesson 10, we are going to be learning about another set of solutions. So we know about one solution, and we just learned about infinitely many solutions, where our constant term and our linear term are the same on both sides. We're going to be learning about a third one called no solution, and we are going to talk about what characteristics there are for no solution. So starting with the riddle, it says that suppose I multiply a mystery number by 3, add 10, then subtract the mystery number, and the result is to be 12 more than twice the mystery number. What could the mystery number be? So we have done this before, where we translate the words that they give us, translating them into a math expression. So we don't know what the number is. So we're just going to say n or 1n, and we are going to multiply it by 3, add 10, and then it says subtract the mystery number. So our mystery number was 1n, so we are going to subtract 1n. And then it says the result, which is another way of saying equal. The result is 12 more than twice the number, the mystery number. So that is 2n plus 12. And then simplifying what we have in our expression, we know the 1n times 3 is going to give us 3n. Then we have 3n plus 10 minus 1n is equal to 2n plus 12. And we're just going to keep simplifying. We now have 3n minus 1n plus 10, still equal to 2n plus 12. And then finally, for our last part, 3n minus 1n is 2n plus 10 is equal to 2n plus 12. Now, when we talked about infinitely many solutions, we said that we have the same linear term and the same constant term. But you'll notice with this one, we have the same linear term, but we have two different constant terms. And what happens with problems like this, where if we have the same linear term but a different constant term, this is what results in no solution. So when we have the same linear term, same constant term, that is infinitely many solutions. That means any number could work. But if we have the same linear term but different constant terms, like what we have with this one here, then it is going to be considered no solution, meaning there is no number that exists that when we plug it into our equation is going to give us the same thing on both sides. Even if we were to plug in a number for this expression, we would not get two numbers that are equal to each other when we simplified to the very end. So keeping that in mind for linear terms, if our linear terms are the same, constant terms are the same, infinite solutions. If our linear terms are the same, different constant term, no solution. So with these examples that we have here, you don't have this directly into your book, but you will get a copy of this. We are going to go through and solve for each of these, and then just making sure that you're understanding the difference between what an equation looks like in its simplest form. That is going to let us know that it is infinitely many solutions, no solution, and then of course the very first one that we learned about, which was one solution. So for this one, we have 3 times 4n plus 3 minus 3n is equal to 2 plus 9n minus 11. And for our first part of this one, this is what it looks like when we use our distributive property. So we have our 3 times 4n, all of this going across. And as we are solving, we now have 12n plus 9 minus 3n, everything going across. And from here, simplifying 12 minus 3n, and now we have the 9n and then the 2 minus 11. So we're just rewriting so that we have our similar terms together. And then we get for our last part here, we have 9n plus 9, because 12n minus 3n gave us 9n plus 9, and 9n minus 9. So for this one, our linear terms are the same. Both of them are 9n. But for our constant term, we have a positive 9 or a plus 9, and this is a minus 9. So would this one be considered an infinitely many solutions, or would this be considered no solution? Going on to the next one, putting together our like terms. So we grouped together the 1/4 and the 3/4, kept our 1 out to the outside, and we didn't have anything to simplify on the second side. And 1/4 plus 3/4 gave us 1d, or 1/4 d plus 3/4 d gave us 1d. We have 1d plus 1 is equal to 1d plus 5. And for this one here, same thing. Our linear terms are 1d and 1d. Our constant terms are 1 and 5. Would this be considered an example of infinitely many solutions or no solution? Going on to the next one, we have negative 4x plus 5 is equal to 5 minus negative 4x. And actually, rewriting our additive inverse so that we can clearly see what the signs are for our linear term and our constant term. So for this one here, we see that we have our linear term is negative 4x and negative 4x, and our constant term is 5 and 5. So would this one be considered a infinitely many solutions, or would this one be considered no solution? Going on to the next one, we have 9m minus 6 is equal to 6m minus 9. For this one here, the 9m minus 6 could also be written as 9m plus negative 6. And the 6m minus 9 can also be written as 6m plus a negative 9. So our linear terms, we have 9m and we have 6m. And then we have a negative 6 and a negative 9. For this example here, this would be considered, this is not going to be no solution because our linear terms aren't the same. It's also not going to be infinitely many solutions because we don't have the same linear and constant term on each side. So for one like this, where our linear terms are different, this is going to be considered one solution. For the next one, we've got 10r plus negative 2 and 10r plus 1. Identifying, are your linear terms the same? Are your constant terms the same? Figuring out for this one if this is going to be infinitely many solutions or no solution. And for the last one, whenever you see a negative out on the outside, we've talked about invisible terms before, so this is a negative 1. And we're going to distribute that negative 1 to everything that is in parentheses here. So we have negative 1 and 4y plus negative 1 and 7. Reading through this whole thing, when it is simplified for this one, we are left with negative 4w, plus 7 plus 3 is equal to 10 plus negative 4w. And simplified, this is what we get after we combine our like terms, looking at what your linear term is for the both of these and looking at what your constant term is for each of these. Do you have the same for both or is something different? And answering, is this going to be is this going to be no solution or infinitely many solutions? And you're actually going to sort down at the bottom because I've been asking you throughout the video which is which. So you are going to take whatever the simplified version of each of these expressions are. Once you know which of these solutions they are, you're going to put them into this table down at the bottom. Just writing the new simplified version of each expression is what goes here. And then for our last part, you're going to create an equation on your own. It says choose values from the boxes to create an equation with the given number of solutions, then write the equation you created. So the very first one they want you to do is only one solution. So remember, with only one solution, your linear terms are going to be different. It does not matter what your constant terms are. The only thing that matters for one solution is that your linear terms are different. So you are going to figure out if this is your linear term and your constant term, what can't your linear term be? And your constant term could be anything because the only thing that matters is your linear term. For infinitely many solutions, remember that your linear terms and your constant terms are identical to each other. They are equal to the exact same thing. So what values would have to go in the box for this one here? And for the last one, for no solution, remember your linear terms are identical, but your constant terms are different. So what would your linear term have to be? And what would your constant term have to be? Or what could it be in order for this one to be considered no solution? And for our last part, for number 4, it says to choose values for a and b to create an equation with the given number of solutions, then write the equation you created. So we are doing the exact same thing with number 4. You're going to create an example where you have only one solution, create an example where you have infinitely many solutions, and then creating an example where you have no solution. And this concludes lesson 10 of module 2.